Okay, now it's the time to start the session. Good evening, everyone. Welcome to the keynote session of the day 2. My name is George Maeda from Tokyo University of Science. It is my great pleasure to chair this session and introduce wonderful speakers. I believe you will enjoy the session and be inspired by interesting talks. Now let's start the session. The first talk will be given by Professor Jim Kurose from University of Massachusetts, Amherst. I will give a brief introduction of Professor Kurose. He's now a distinguished university professor of computer science and associate chancellor for partnerships and innovation at the University of Massachusetts, Amherst. He received his PhD in computer science from Columbia University and BA in physics from Wesleyan University. His research interests include computer network architecture and protocols, network measurement, and multimedia communication. He has been a visiting researcher at many institutes, including IBM and Sorbonne University in France. From 2015 and 2019, he served as assistant director at the National Science Foundation, and in 2018, serving as an assistant director in the White House Office of Science and Technology Policy. He has received a number of awards for his various activities, including the IEEE Infocom Award, SEM Syncom Lifetime Achievement Award, IEEE Taylor Booth Education Medal, and the CRE Distinguished Service Award, and so on. His keynote speech today is the software-ization of networking protocols, people, pedagogy. So Professor Kurose, please start your talk if you're ready.
Thank you very much. Can you hear me okay?
Yes, perfect.
Okay, wonderful. Well, thank you very much. I'm very honored to be able to present a keynote talk here and wanted to thank Professor Maeda and Toshio for the invitation to speak here. I've visited Japan many times. I'm Japanese by ethnicity. My grandparents are from the Okayama-ken area of Japan, and I've visited Japan many times, had researchers from Japan come and stay in my lab, and so it's really a personal honor to be able to talk to all of you today. What I wanted to do was talk to you about a theme I see going on in networking. I'm sure many of you have sensed this too, about networking becoming more and more about software. And this talk is really just some reflections on that. And again, I'm very honored to be able to share it with you and would love to hear folks' thoughts on this also. So I have a talk that should run about a half hour, and I hope we'll have time at the end for some questions and conversation. So I'm going to share my screen here. And just start up my slides. Okay, you can see my slides okay?
Yes, okay.
Okay, wonderful. Okay, so it's a little bit hard of a phrase to translate from English into Japanese, but there's a saying in the United States in English about software eating the world, and you can think of it as taking over the world. And I want to talk a little bit about that quote and where it comes from, and then talk a little bit about protocols, what this means for protocols, for people, and for pedagogy. So this phrase, software is eating the world, came out about 10 years ago. And I want to start this talk with 3 quotes. And this first one is this saying that software is eating the world. It was made by Mark Andreessen, who many of you may know is the inventor of Mosaic, the first internet browser. He co-founded Netscape. He's a venture capitalist and actually a thinker about all trends in computing. And he said software is eating the world. And what that meant was that there was this wave starting in 2008, 9, 10, 11. There was a wave of global software-enabled companies like Amazon and Netflix and Google, in financial services like Fidelity, for example, and that these companies their services are all based in software. So you could make them very quickly. You could adapt them very quickly to what customers wanted, and that it was this advantage of having software that made these companies, or being based in software, that made these companies so well, valuable, but also nimble, the ability to change. So this is the first quote that I wanted to start with: software is eating the world. Here's the second quote, and this is from a friend of mine, Nick McEwen, who some of you may know as really one of the principal architects and thinkers behind software-defined networking. He was a professor at Stanford for many years, and now he's a vice president at Intel. And here's his quote. He said, in 2030, so this was a talk he gave maybe a year or two ago, he said, in 2030, networking students will learn how to program a network top-down as a distributed computing platform. And here's the sentence that has caused me to do a lot of thinking over the last 2 years. And that is, he said that protocols will be described in quaint, that means old-fashioned, old language, historical terms. Protocols will be described in quaint, historical terms. And that got me really thinking, because the third quote comes from me. And this is a quote, it was something that I wrote in probably 1998 when we were writing the first edition of our textbook. And it's a sentence that has been unchanged in our textbook for almost 25 years now. And my quote is that protocols are running everywhere in the internet, and consequently, much of this book is about computer network protocols. And in fact, the book really, our book, Computer Networking: A Top-Down Approach, really is a lot about protocols, as this quote from the very first beginning of the first chapter says. So these three quotes sort of form, I don't know, the ideas that are swirling around in my head to get me thinking about protocols, software, where internet architecture is heading. And so let me get started, because I want to first talk about protocols. And I almost had a title for this talk called "Are Protocols Dead?" And that's because of Nick McEwen's talk. Remember, he said protocols will be described in quaint historical terms. Historical meaning nobody really needs to know about them anymore. They're old-fashioned. They were used 10 years ago. And so the first question I want to ask is, are protocols dead? I mean, that's basically what Nick McEwen was saying. Okay, so just by way of background, I know many of you know this. For others of you who are maybe coming more from the physical layer, maybe this will be helpful. But traditionally, I want to sort of start with a traditional view of how in-network control and management is done, okay? And it's typically done in a distributed, sort of local view, like the actions are taken by these local routers and local entities inside a network. So let's take an example of routing and forwarding. So every router, here's a small toy network with routers. Inside the routers are forwarding tables that say, oh, well, if a packet comes in with this header field, send it out this way, right? Network routing has been done this way now for 50 years. This is the way routing tables, well, there have been routing tables, forwarding tables, and how they're computed is inside each and every router. So open up a router, you've got a routing protocol. So you've got RIP or OSPF for an intra-domain routing protocol. And they're exchanging messages with each other. They perform a local computation. And from the messages they exchange, they create the forwarding table. Okay. And so we have a clear distinction here. Inside each and every router, there's a data plane sort of at the lower layer. And then we have a control plane, which is basically a distributed computation that's done using protocols. And so in traditional networking, there are many protocols ICE and OSPF and IBGP, which are the intra-domain protocols. For example, on the right, there's BGP, inter-domain, HTTP dash at the application layer, TCP, obviously, IP, the wireless protocol 802.11 and various other protocols, and network management protocols as well. So, when I reflect back on the quote from my original, that I originally wrote, I do believe that today protocols are really running everywhere in the internet. But that's the traditional view of in-network control and management. Let's take a look at what software-defined networking is all about. So software-defined networking takes what's called a logically centralized, meaning it could be a distributed computation that happens in a data center, for example, but that it looks like a logically centralized, it's in one place, but it might be distributed in that one place. It takes a logically centralized management approach that has a network-wide as opposed to a local view. Remember, protocols are based on local views. SDN is based on a network-wide view, as we'll see. So in software-defined networking, you've got a remote controller. It might be off in a data center somewhere. So the brains, the management plane, if you will, is being taken out of the routers and moved to these remote data centers, right? So routers become, in a sense, dumber devices. If we look at the routing example, we see the forwarding tables are actually computed remotely, and then they're downloaded into the routers, right? So the brains, if you will, are in these remote data centers. So we've got a logically centralized device and flow configuration and management protocols now that happen in SDN. So the control plane is implemented outside of the routers, outside of the switches, outside of the links, in some remote data center, which has this global view of what's happening in the network. We've still got the data plane. The data plane now is dumb and fast, implemented in hardware. If you think about that, what happens inside a router, we've sort of taken the intelligence out of it, if you will, or the computation out of it for the most part, and put it in these remote data centers. Because you've got this logically centralized view of what's happening in the network, makes it a lot easier now to start thinking about network-wide properties. For instance, are services reachable? Are hosts reachable? Are there routing loops? If I've got VPNs, do I have virtual private networks? Do I have isolation among those? Do I have the right kind of access control within the network? All of the information that you need to reason about those properties of correctness or correct configuration, for example, are all present there in the data center. So it just becomes these very difficult properties to check for in a traditional sense, just become, well, something that you compute over, some data that you compute over in a data center. So some things become potentially very, very easy. So I want to make the case that the migration from protocols is already well underway. So we've heard about SDN, certainly in the news, but in some ways, it's really happening there at production scale. So here's an example. Google has their control plane is their new control plane. It's called Orion. It takes the control plane that they had for data centers, which was called Jupiter, and their wide area Google internal wide area networks that was called B4, and they're combined now into one SDN, one software-defined network controller that you see over here at the right. So over here on the right, this is the logically centralized view. This is the control plane that Google uses for its combined data center and networks, okay? So it's that logically centralized control plane that we were just talking about in SDN. So this is what Google is doing now. So let's ask ourselves, well, what about routing protocols? The intradomain, the IBGP, for doing traffic engineering, where should flows go? Are these implemented by protocols? No, there are no routing protocols in the Orion control plane. So inside the Google data centers and the Google's B4 wide area network. The routing protocols are being replaced by a computation in a routing engine that you see over here on the right-hand side. Hopefully you can see my mouse over there. So we've got a routing engine that's implementing algorithms, not protocols anymore. Let's take another example. Oops. Take another example. Think about flow control. This is another classic, congestion control protocol in the internet. Is it implemented by a protocol? No, it's implemented by a piece of code running inside Orion, a flow manager, which now allows explicit mappings of flows along given paths with given flow rates from one endpoint in the network to another, and allows Google to do that in a way that allows them to meet their contract service level agreements. So we've seen routing protocols being replaced by routing computations in the SDN control center. We've seen flow control now being replaced by algorithms being implemented in this logically centralized way. And if we think about management, well, management is done by a pub sub, what's called a pub sub type of architecture, microservices, all inside the Orion core. So protocols like SNMP, for example, they don't operate network-wide the way they used to. All this management is happening through pub sub distributed microservices inside the Orion core. Okay. And so I will note that Orion provides only for the intra-domain within the combination of Google data centers and the Google's wide area network within Google's network. So we see that this migration away from protocols is already underway. And so you look at that, or I look at that, and I say, well, I'm thinking back to what Nick McEwen said at the beginning of the talk. Will we still need protocols in 2030, 8 years from now? Are we still going to have protocols? So I've been thinking about this question a lot recently, over the last year and a half. Are protocols really dead? And so I've come to, and matter of fact, we've seen Google doesn't, in Orion and in Google's B4 network, there are no routing protocols. There are no congestion control protocols or flow control protocols. There are very few management protocols, right? It's all being done just by computations inside the data center. So our protocol's dead. So the answer that I've come to is that, yes, protocols are still needed, but actually I do think they're not going to play as important a role. And so the question I've been asking myself is, why do we need protocols, and where will we still need protocols in the internet in 2030? And I'll show you my answers. I'm still thinking about this, so not quite sure this is right or not. So the key thing where we will always in some way need protocols is in an internetworking sense. When you have two organizations coming together, they need to communicate with each other. They've got separate control planes. So think about eBGP, think about mobile packet cores in different organizations in a 5G network, for instance, that need to talk to each other. There still need to be protocols that govern how entities in different organizations talk to each other. We're going to need that at the application layer because, for example, my device, my web browser that I'm using right here, that's being attached to a server somewhere else, are in different organizations. So you look at a protocol like HTTP3, that's not going to go away either because they're not configurable end to end. And we're going to need these for identity management, for setting up connections. So for instance, in 802.11, to do the beaconing in 4G, 5G networks, you're going to need home location registers, home services, and protocols like Diameter for being able to do identity management, to do the initial connection, to establish what the capabilities are, to establish trust between entities in two organizations that didn't know each other. So for me in the future, protocols are going to be all about entities coming together from different organizations that need to interact. And within an organization, within a network that belongs to one organization, I also think that protocols are mostly going to be going away. Okay, so just one last thought here. I've been thinking also about this, how the protocol stack and interest in the internet and research interest in the protocol stack has been changing over time. And I want to show you this mostly because of where I think we are today. So pre-2000, I would say there was a lot of emphasis on the network as an artifact, something that we built, what's its performance? And there was a lot of interest at the network layer, the transport layer. This is what's called a heat map over here. The dark colors mean intense interest. From 2000 to 2008, we saw distributed applications, issues like mobility, security coming to the forefront, and we see applications, HTTP, for example, really coming to the forefront here. In 2008, where we saw the first data centers, to 2020, data centers, mobility, security, privacy, and I want to say this is where management, so SDN from 2008 onward, configuration management becomes very important. And then I'll say finally, IoT, mobility, again, management, what's happening between the edge and the core, and the edge, the core, and the end user, and integration with the cloud, and even more emphasis again here on management is what we're seeing. Okay, so that's the protocols piece. Again, protocols are not dead, but where they're going to exist is changing. Okay, so I want to say a couple words about people, and then pedagogy, and then I'll be done. So with respect to people, I want to talk about this theme of taking people out of the network management loop. And this again is being enabled by software-defined networking. And this picture over here is an SDN picture. You see an SDN controller here. At the top of this sort of conceptual management diagram, you have inputs to the SDN controller, and then down below you've got the switches, the operating systems, the hosts that are being configured, and where you're doing fine-grained telemetry, where you're doing fine-grained measurement. And in something called intent-based networking, what's done is one specifies in a high-level language properties that you want the network to have. Okay, so that's here. These are then compiled down sort of automatically into configurations that satisfy this high-level intent here. And then again, using the SDN controller that we saw before, the configurations are then pushed down here to the host devices here. Measurements are made to make sure that the intent is being met. They're fed back here to do runtime verification. And so you've got sort of one loop here and then another loop here. Okay, so we're specifying the management and the design changes by what we want to do rather than how. And that's a profound change in network management. Network management has always been about how, as humans, to make the network components do this, do this, do this. And now it's high-level intent using compilers to go from high-level intent to the actual configuration that's needed. So if we think about timescales, this high-level intent here does not change at rapid timescales. We've got these lower level intent and detailed configuration changes that are compiled, again, software oriented, software implemented, that are consistent with this high level intent, and we can, again, in an automated way, check for correctness and consistency. So if you think about what's the role of people here, you can see that the people come in basically up here, specifying the high level intent, but this closed loop control, this is all compiled in, so that from a network management point of view, you don't have network managers who are using SSH to get into a router and then typing CLI into a router. They're not configuring the individual routers. Network managers are specifying this high-level intent, but the devices, their settings are all being configured completely by software through this compilation process here. And so, as a network manager, the secret sauce, the competitive advantage you have is in how you compile and create that higher level intent. Everything after that is completely automated. And I want to give you one example of a paper that hasn't been referenced that much, but I just loved, that came out of Bell Laboratories, I think 2 or 3 years ago here. And this is just an example of sort of this intent-based networking and this closed loop of monitoring, verification, and then change. Okay. So they have something called in Bell Labs. Actually, here's the paper here from this group in Bell Laboratories. They have something called a verification transverse. So what you specify are service level agreements at a high level. You're specifying them using temporal logic. So those are the properties you want your users to experience, the SLA, the service level agreement. Okay. Then what happens is in an SDN environment, the network settings, the routes, the flow control, the congestion control is all compiled and determined, pushed down from the SDN control center into the routers. And then there's measurements that take place here to check the fine-grained performance measurements against the SLA. And if the SLA is violated, some kind of action is taken. So I really loved this paper. It's one of the first working examples I've seen, and it's in a small network, granted, but I think this is where a lot of research is headed. It's a small example of this notion of intent-based networking and then compiling down what configurations look like from there. Okay, so I'm almost done. I just wanted to say a couple words now about pedagogy. That means our teaching. How are we going to teach networking, especially introductory networking? So I know many of you are faculty members or have to educate, have to teach the workers that you're working with. So what goes in an introductory computer networks course, given this change, this softwareization of networking? Okay, so this is a picture of the first edition of our textbook, which took a top-down approach. I know it's used widely in Japan. We took sort of a computer science view, a top-down view, starting with the application layer, then going down to the transport network link and physical layer. And this reflected, in my mind, the computer science view, thinking about abstractions, if you will, the APIs versus bottom up, starting with, oh, we've got a link, how do we communicate over a link, and then building up. That's the way networking used to be taught. It's more of an electrical engineering view, I think, than a computer science top-down view. So in a software-defined world now, think about the softwareization of networking. What does this mean? Well, in 2015, in our textbook, I finally thought, we have to start teaching software-defined networking to students because it's becoming so important. So we took the network layer and divided it up into two parts: a data plane that has generalized forwarding at high speeds, open flow as a protocol, and then a control plane where we looked at routing algorithms, not routing protocols. Well, we looked at routing algorithms and their implementation in either protocols or in an SDN controller. We talked about data models as a way to being able to compile what configurations would look like. So if I were to summarize here, I would say that protocols are not quite dead. We're going to always need these at the application layer for internetworking, for management. Coming back to this picture here, you see how fat and how important this management and network configuration piece is, the application piece. In the network layer, in the transport layer, and in the link layer, maybe not quite so much in the link layer, I think we see the move afoot to change from distributed protocols to algorithms. I think that's going to be a very important change. And we see this notion of distributed systems coming to the front, right? That we're going to be designing now these software-defined network controllers that are going to be distributed for scale and for robustness. We're going to need to worry about the edge, core, how these different pieces of the higher level network computations happen, and then identity management is going to be important. And then, well, if this is where things are happening, what are we going to teach, right? And well, we're starting to work on the 9th edition of our textbook, and I think the next edition of our textbook will reflect even more this view of the softwareization of networking. So let me finish with just one closing thought here. And that is the network softwareization, I think, opens up a lot of opportunities. It allows us to build algorithms in sort of a more traditional, to build functionality in a more traditional computer science way of thinking of the world. Just what are the algorithms? Not what are the protocols, what are the algorithms? It allows us to develop and build our ideas on top of open and disaggregated software. So if I think about a mobile packet core, I can think about open source platforms like ORAN and Ether, and then testbeds like the Powder testbed that's part of NSF's Power initiative here. And it now allows us to be doing everything that we're wanting to do in algorithms and in software that are implemented in and on top of this open and disaggregated software. Okay, so I think I'll skip over this last piece. This was just about sort of a long-term history of networking, how over time, the abstractions have gone from sort of the bottom of the network, the circuits, then the packets, then the flows and flow control and protocols, really up to these higher level issues of content, manageability, quality of experience. I think all of these are becoming more network-wide abstractions and more logically centralized, more softwareized abstractions. Okay, and I think with that, I'll stop again. I want to thank you for the great honor of being able to present a keynote presentation at this meeting. And let me stop there and just see if there are any comments or questions that people might have. Thank you very much.
Thank you, Professor Kurose. So it's a time to accept the Q&A session. So
Can I?
yes, sir, please.
Oh, thank you so much for your great talk. And I'm afraid that I misunderstood your talk, but you said that our protocol will be replaced by kind of centralized control software, but still remains in the inter-AS or inter-autonomous entities.
Right.
And in that case, but the softwareization is if intent-based softwareization control is enabled for intra-networking, but current inter-AS protocol is very old-fashioned, and that protocol not enable intent-based intent coordination or not. So,
Right.
is there any chance to make a new protocol that enable intent coordination among the inter-AS between AS or
Right.
so yeah.
That's a great question, and I think you understood completely what I said. There was a I don't know how many people have seen this, but there's an event, an every 2-week event on something called the networking channel. So if you Google networking channel, no spaces, just networking channel .eu, there's a seminar that we run every 2 weeks, and last week, or now maybe 3 weeks ago, we had one on software-defined networking, and it was organized by Bruce Davey, who's in Australia, and there were 2 Japanese network engineers who were part of that. And I asked them that exact same question, because one was working for VMware, and another was working with a lot of ISPs. And I'll tell you his answer, because I've wondered this exact same question. So BGP is sort of that glue that holds together the different ASs in the internet. And you might wonder, BGP is now 25, BGP4 is 25 years old, right? So will there be something new? Will there be SDN, inter-AS SDN? That was the question I asked him. And his comment, I still remember it, was, whenever he hears the word inter anything, it's very, very hard, right? Because you have to get organizations to agree on things. So his comment was that he didn't see that happening, and he knows more about what's happening in practice than I do. Let me tell you something that I see potentially happening. There's a saying that the internet is flattening, that the number of network hops you have to go through from a source to a destination is getting very small. So when I watch YouTube, the only networks I cross are Google and Comcast, which is a big cable network in the United States. So for a lot of my services, I go through only 2, or Netflix, for example, I only go through 2 ASs. So maybe it's possible that ASs that trust each other will agree to share a piece of their control plane with each other to build a for certain paths, for certain sets of ASs, an end-to-end SDN-ish type of approach. But I think to share your control plane or share control plane information, there has to be a great deal of trust between 2 organizations. So I think maybe if we see this, it's a great question. If we see this, I think where we'll see it first is between those larger organizations that peer with each other and have a good deal of technical trust in each other.
As the internet is more flattened, then multi-party negotiation is not needed, but bi-party negotiation is enough. And in that case, the kind of privacy, secret preserving negotiation might enable such a protocol. Internet-based. Thank you.
Right.
Okay.
Yeah, I think it's absolutely possible. But what I've been thinking about recently is, what are the advantages of doing that? So I see the advantages of configuring a network and managing a network in a logically centralized point of view. Notice I never say the word centralized. I always say logically centralized. I'm not sure that that if you take Google and Comcast coming together, whether sharing between them, there's enough of a win there to overcome the complexity of doing that. I think that's the question. So the question is, how big are the wins? How big are the advantages of doing something end to end?
Okay, thank you so much. Thank you.
Thank you.
Thank you. And any other questions from the audience? How about from online audience? Yes, please.
Thank you very much. Very informative talk. So I have a
you.
question. So many people here is discussing 5G or beyond 5G and 6G era. So if possible, please give us some suggestions. What kind of protocol research is the most important, do you think?
So that's a great question. I have been thinking a lot about that myself. You probably saw as we've gone from 4G to 5G that there's been, so 5G very much adopts this notion of software-defined networking as the implementation mechanism for the control plane. So I think that, and if you look at mobile packet cores, if you look at, for instance, Microsoft, for example, has something called Azure for Operators. And so Azure for Operators is Microsoft saying to an operator like AT&T. So AT&T and Microsoft signed an agreement that in principle, Azure, the data center solutions from Microsoft combined with AT&T's network can sort of provide that combined network management with operations. And so you think about AT&T's wireless network, for example, I do think it will be very, very much a softwareized control plane, where I think there are interesting, I'll tell you some of the interesting research questions that I see there. So I believe, first of all, that the softwareization of 5G and beyond absolutely will happen, as you were suggesting. Here's an interesting thought experiment for you. One of the things that are unique about wireless networks is that they coexist, different wireless networks coexist in space. So, for instance, if you have an AT&T and a Verizon wireless network, they overlap in space outside my window here, for example. So imagine you have two devices. One is attached to the AT&T network, and one is attached wirelessly through 5G to the Verizon network. And imagine those two devices want to communicate to each other. To communicate, they have to go, well, obviously across the link into the mobile packet core, from the mobile packet core all the way up into an IXP or whatever the interconnection mechanism is. And so you have two devices that are physically next to each other and may even be interacting with each other. And yet to communicate, they have to take a many tens of millisecond, hundreds of millisecond loop from the links up into their mobile packet cores, up into the wired backbones, up to an IXP, and then over to each other. And I think that notion of how you implement local communication among devices, and now I'm thinking IoT devices, for example, between IoT devices that exist in different networks, that's a research question, for example, that I've been thinking of. But I think, again, IoT opens up a lot of interesting research questions there. And again, this question of where the computation is and what data the computation has, given that it's inside a mobile packet core, just makes for lots of really interesting research questions.
Okay, thank you very much. Thank you.
One question.
I see a question from Mickey Yamamoto. Hi, Mickey.
Yeah. Hi, Jim. Thank you for your talk. I understood and fully agreed with your opinion from the computer science view. And for example, in Google, they would like to use the commodity switch because it's very inexpensive. In that sense, standardization plays an important role.
Yes.
So I'd like to hear about your opinion about the standardization where the standardization will go in 2030?
Okay, so that's a great question. It's true that it's true that standards drive everything. I'm going to answer your question in two ways. I'm going to answer it first, maybe in a general sense, and then I'm going to answer it from a research sense. So I think in a general sense, you know, when you have standards, the important things are what are the APIs, right? So if you think about OpenFlow, for example, and the standards are, you know, simply have to do with, well, if you're going to push down forwarding tables, you're going to use OpenFlow or SNMP or NetConf. And so you're going to use one of these protocols to push down forwarding tables that have this format. And I think that kind of standardization is happening already. I mean, there are what are called white box devices that actually do that. So I think in that sense, I think for the forwarding plane, that's already happening. If you look at the 5G standards, I mean, the 5G standards are really all about interfaces, right? So it doesn't really matter how you're implementing what's on the other side of the interface, so long as you're able to program to the API there. So I think, you know, the standards will come along. I want to pass something on to you, Mickey, that maybe I shouldn't name the person who said it, but he's a well-known networking person, and he's also very high up in a US company that does data centers. I'll just say that. And we were talking about this issue of standards, and we were talking about open source. And he was telling me and, I don't know, 4 or 5 other people who were standing around talking with him. We were asking him the question you just asked me about standards and actually influencing standards. And his suggestion to us was standards are now, I don't know, going to the IETF, for example, or 3GPP. I mean, these are big corporate, I don't want to say controlled, but, you know, the big players there are the corporations who have lots of money and have lots of reasons for the technical directions to go in a certain way. What he told us, which I thought was pretty interesting, Mickey, was that for us as researchers, he thought that the best way to go was to be dealing with open source, because you can make the changes in open source, you can get the changes out there, and then they can be adopted or not. So build on top of open source or change the open source. And so, you know, for me as a researcher, I mentioned Ether, for example, that comes from which is, you know, open source software. That for me, we're building a lab here that's built on this open source 5G open source, so we can do those kinds of research experiments that I was talking about in response to the earlier question about when you have overlapping networks, how might you be able to do things? So I think that there are ways to, as a researcher for you, there are ways to affect how people do things, and the way to be doing that is through open source, because I think one of the challenges that we face is, as researchers, is that it's hard to do things in the software side of wireless, you know, of 5G systems, because the commercial systems are owned by companies who are operating them as products, but the open source and the new licensing of spectrum, at least here in the United States, allows parts of the spectrum to be used. You know, you don't have to purchase access to that spectrum, so you can do that kind of experimentation. And there are both handsets, you know, iPhones, for example, and open source implementations of 5G, nearly complete 5G and complete 4G functionality that you can now get at the edge.
But the standardization has the strong relationship to a protocol, right? No.
Oh, yeah. So, yeah.
So I mean, you mentioned protocol is not so important in future. However, if standardization plays an important role, protocol also plays an important role.
Yeah, so that's a really good question. And I think that that is absolutely still true in, protocols won't go away, right? So there will always be, if even for legacy, I mean, that's what Nick McEwen's quote was about. Let me first talk about this in the wired internet sense, and then we can take it into 5G, right? TCP will not go away. And ISIS as an intra-domain routing protocol won't go away. It's just that more and more that will not be the way in which routes are computed intra-domain, right? I'm absolutely convinced of that you'll still have ISIS and OSPF, but they'll just be used less and less, right? If we take that into the 5G and you think about all the interfaces that are defined, those interfaces are defined because there are vendors who are currently, offering different pieces of 5G solutions that you can plug and play the different pieces together because they're, because of the well-defined interfaces between all the pieces. To me, the question will become, will there be white box functionality in a 5G, 6G, and beyond sense that allows the software, well, not the softwareization, but allows the central computation to be happening more and more in a data center, in an SDN, and results to be pushed out into those individual units so that some of the protocols that operate across those interfaces aren't needed all the time anymore. I agree with you 100%. They are needed now.
I see. Yeah. I feel a little bit relief because the protocol is not dead. So thank you very much.
Okay, thank you for the question, Mickey.
Sensei. So it's time to go to the next talk. So thank you very much, Professor Kurose. Let's thank to Professor Kurose again.
Thank you again.
Thank you,